You can see from our previous discussion that buffer management plays a key role in talking about recovery, atomicity, and durability. We tried having a no-steal policy. That's the terminology used in the literature. We didn't allow buffer pool frames with uncommitted updates to be replaced or otherwise flushed to disk. And this is, we thought, useful for achieving atomicity without needing to be able to undo stuff. So we didn't need undo logging because we would never write anything we would want to undo. One of the problems with the no-steal policy is it can cause poor performance because these pinned pages limit buffer replacement, as we discussed. We also tried a force policy, that's terminology from the literature, where we made sure that every update is forced onto the database disk before commit. So we didn't commit until all the pages of the transaction were forced down to the database disk. And this provided durability, and we didn't need any redo logging. We didn't need to be able to do anything after the system comes back up to make sure that committed pages were really on the disk. But the force policy also causes poor performance, which we haven't discussed yet. In order to write all those transactional pages to the database, we had to do lots of random IOs before we committed. Every dirty page had to be written to the database. Dirty pages could be in all sorts of random locations in the database. And our updates to those pages might have been very small. We might have changed only one bit on each page, but we were doing a lot of IOs to transfer those small deltas down to the disk. So our simple idea that we looked at was a no-steal force policy, which was supposed to make things simple. But we, even there, didn't really achieve atomicity. We had a baked-in assumption that we could do all our forcing atomically, which wasn't really true, right? We can't force all those pages to disk atomically. Okay. So our preferred policy is going to be the opposite. It's going to be steal, no force. So let's look at the design space here. This is the most complicated but highest performance option. So we're going to really go for it here to try to make things fast. The no force policy is going to complicate the enforcement of durability. The problem is system crash before a dirty buffer page of a committed transaction is flushed to the database disk, right? We have a dirty page in the buffer pool. We have a committed transaction, but that dirty page has yet to be written to disk. How do we get durability? The solution is somewhere, somehow, we're going to flush as little information as we can in some convenient place prior to commit. This is going to be called the log, and this is going to allow us to redo the actions of a transaction upon crash. So if we say commit, somewhere on the side we've written down all the things we did during that transaction so we can redo them. The steal policy is going to complicate enforcing atomicity. What if a transaction that flushed updates to the database disk aborts? Or what if the system crashes before the transaction's finished and dirty pages have been flushed to the database? For this, we have to remember the old value of the flushed pages to support undoing the write to those pages. And so we'll need to write down somewhere convenient the old versions of pages so that we can undo updates that shouldn't have been done. So as the note on the lower left has been saying while we've been going through this, this is a dense slide, and it's really the crux of this whole lecture. So you should read it over carefully and return to it after we go through all the mechanisms and convince yourself of how we've achieved a no-force steal policy using the protocol we're going to learn. To summarize, we've got this kind of design space of force, no force, steal, no steal. It would seem like the slowest but simplest thing to do is force, no steal. That was our first idea. And the fastest thing, the thing we just described, would be steal, no force. You can, in principle, try to do the other corners, okay? In steal, no force, in the upper right, the logging and recovery implications are we have to have undo and redo logging. In force, no steal, the lower left, we didn't need any kind of logging. And the other two boxes represent the kind of logging we need if we leave out one of those things. So in a no force, no steal box in the upper left, we don't need to do undo because pages are never stolen by the buffer pool and we never write dirty data to the disk. Okay, but we do need redo because we commit without flushing the pages to the disk. And in the lower right, in a force steal scenario, we need undo logging because pages can get stolen and flushed before the transaction commits. But we don't need redo information because we're going to force all pages to the database before we commit. Right? But as we said, the highest performance goal is in the upper right, and it's going to require both undo and redo logging, and that's what we're going to learn about next.